everybody. My name is Héctor. I'm going to be talking about the climates of GL514b. This is a work I've been doing with Rory Barnes from University of Washington and Russell Dietrich and Mario Damaso. To give you an outline, I'm going to first give you an introduction and convince you why we study GL514b. I'm going to show you what are the factors that we consider that affect habitability. Then I'll show you the methods that we use, and then the results, followed by conclusion and the future works that are deemed important to continue doing. So why study this planet? In 2022, Mario Damaso and his collaborators, they discovered GL514b. And what's particular about it, it's that it has a high eccentricity. Eccentricity, it's how circular the orbit is. And when it's a high eccentricity, that means that the orbit is kind of like an oval shape. And usually when we study exoplanets, we look for planets that are within the habitable zone. And this planet, because it's very oval shaped, it kind of falls in and out of the habitable zone. So that makes it a particular object to study. It also, as you can see from the properties, it also orbits an M-dwarf star, which is the most abundant star in our galaxy and universe. And with that in mind, when we look at the multiple orbits that could happen in this planet, these are just simulations of what a 0.45 eccentricity orbit would look like. We see that they all go in and out of this green shaded region, which is the habitable zone, that we consider the habitable zone of the star. And the dashed line is just the best fit orbit. We still see it, all of them go through in and out. So that's what makes it very important to study for habitability, since we've never done that before. And another reason why we want to study GL514b, in this graph I'm showing you here a plot of the eccentricity over the orbital period of the planet. So how long it takes the planet to go around its host star. The size of the bubbles, it shows how much solar installation or how much of radiation from the star is falling into the planet. On the top right corner, you can see the bubble for what would be like an Earth installation, so how much sunlight we receive. The bigger the bubble, the more radiation the planet is receiving. Gray dots represent we don't have data for the installation, so they don't show any information about that. But in particular, when we look at GL514b, which is in the middle of this graph on the top side, we see that it's almost unique to it. And when we have an orbital period that long around an M-dwarf, it gives us an idea, a better view to use next generation telescopes, such as ground telescopes, to study them and be able to directly observe them. If the planet is too close to the star, the planet would be really hard to see with direct observation. There's another planet that is really far away. We see it at 250 orbital periods on the right side, but it has a low eccentricity, so that's why we don't care much to study that one. There is a planet with 0.5, greater than 0.5 eccentricity, but it has a shorter orbital period than GL514b, so it might be really hard to direct observe, and we want a planet that we can study in the future. And with that in mind, the next generation telescopes, such as the extremely large telescope, it will be a telescope that should be able to observe GL514b. This graph is just showing what is that maximum angular separation that the planet needs in order to be observed, and the planet-to-star flux ratio, meaning that the bigger planet-to-star flux ratio, that means we can observe it better. And in the dashed line, that represents the boundary to be observed to the planets that could be observed with the ELT, the Extremely Large Telescope. And we expect that GL514b will fall within that boundary. So we will plan to use ELT to observe this planet. Now, I hope I convinced you why study GL514b. So now I want to talk about what are some factors affecting habitability. So there's many factors. When we talk about habitability, there's so many things that we can think of. But we focus on the ones that we've seen that in other papers that have shown that these are the most that affect and impact the habitability. And these are the eccentricity that I mentioned, is how oval or circular that orbit is. The obliquity, which is that tilt of the rotational axis from the plane of orbit from the star system. The precession angle is the angle of wobbling of that rotation axis. And the partial pressure of CO2, which is how much CO2 is built up in the atmosphere of the planet. And because it's a 12-minute talk, I don't go into much details as to why them, but those are the papers that we mostly focus that show these are the factors affecting habitability that we want to use for GL514b. We use software called vPlanet, which is an open source code that has 11 physical processes that simulate habitability for a planet. It includes binary systems, includes the radiation from the star, or disturbances in the orbit, disturbances in the rotation, many others. But the one part that we use from vPlanet is the one called POISE, which is an energy balance model. What it essentially means, this graph is a good explanation. I did not do this graph. Trembet and Fasulu did it. And what in essence what it is, it's a balance of all the incoming solar radiation that comes to the planet and how much is that it's either absorbed by the planet or reflected back to space. POISE is a cloud-free energy balance model, so that we don't take into account the reflected sunlight by clouds in the atmosphere. So that means that we mostly focus in two parts of the energy balance model, which is how much is absorbed by the surface of the planet. And on the right side, top side, you can see that it says outgoing long wave radiation. How much of that is being radiated by the atmosphere itself in longer wavelengths. In essence, this is the equation that we use to explain it. In a easy way, I would say that the first term represents that absorption of the heat from the surface. The second term represents how much is being dissipated throughout the atmosphere, so atmospheric circulation of the heat. The third term just shows the irradiation to space, and all of that should balance to the fourth term, which is how much of incoming solar radiation is falling into the planet. So another thing that POISE does, and this is good to know, is that it's not only an energy balance model, but it also calculates the ice sheets, or how much ice it's flowing around the planet. So is the planet covered in full ice? Is the planet just ice-free, meaning that it's all water? Or is the planet has a combination of polar caps or other types of ice configurations, which we deem important for habitability, since we've seen Earth throughout time has how much the ice has changed in that surface. And another part of the vPlanet that we think of is that outgoing long wave radiation. There are many ways, there are many theories on how do we calculate that, how much of that radiation is being dissipated to space. In vPlanet, there's 3 of them, from Spiegel 2009, Williams and Casting 1997, and North and Coakley 1979. So Spiegel and North and Coakley, those two outgoing long wave radiation, they're just as a function of temperature. And Williams and Casting includes a component of partial pressure of CO2. And we can see in this graph how much of that outgoing long wave radiation over surface temperature, it changes as a function of temperature, but with the difference that Williams and Casting, when we change the partial pressure of CO2, in this case, I'm having a partial pressure of simulating Earth's CO2 abundance in the atmosphere, and we see that it gives a more realistic version of how much of that radiation is being dissipated to space. So that means for our purpose of this study, we use Williams and Casting 1997 model to simulate how much radiation is being dissipated. Yeah. Oh, and to say that this Williams and Casting model is only valid from negative 83.15 degrees Celsius to 86.85 degrees Celsius, meaning that anything that goes, if the planet gets too cold or too hot from those boundaries, that means that our calculations of the outgoing long wave radiation are not exactly accurate. So we deem them as, if it's too cold, that the planet is just completely a snowball. And if it's too hot, we just deem it as a planet completely ice-free. In terms of many other parameters, so we're talking about partial pressure of CO2, eccentricity, obliquity, and precession angle. There's other parameters that go into an energy balance model and an ice sheet flow diagram. So here I am just showing you most of the other parameters. Some of them are arbitrary, others are Earth's value. So, as every model, we had to make assumptions, and these are some of the assumptions. For example, the EBM, meaning the energy balance model, we run it seasonally instead of annually. So every season we check that energy balance. We run it for 4 years. So it's run for 4 years, and we run it every 500 years to calculate it. And we use the Williamson-Cassin OLR model, which is outgoing low radiation. The initial global temperature, we use 14.85 degrees Celsius, which represents a pre-industrial Earth's temperature. We have the deposition rate of snow, that's from Earth's value. And then the heat capacity of the land, of the water, and the albedos, they all come also from Earth's value. Now the land fraction, it's analogous, it's similar to Earth. So we use a 25% land, and the 75% is just water cover. It's covered by water. To do our simulations, we divided it into 4 simulations. We first wanted to find values of CO2, eccentricity, obliquity, and precession angle that meet the Philae protocol. I'll explain to you what the Philae protocol is. The second simulation, we studied the latitudinal temperature for various eccentricities. The third one, we did a parameter sweep of eccentricity and obliquities. And the fourth one, we did a parameter sweep of CO2 and obliquity. All of this, we run all the simulations for 1 million years, and I did a total of 960 simulations. Why 960? Just because, no specific reason. And all of these are just static simulations, meaning that the obliquity, eccentricity, and precession angle of the planet are not evolving over time. So that means that for future work, just spoiler, we want to do a dynamic evolution of how we see this eccentricity, obliquity, and precession angle evolve, because we see that on Earth. We see those values changes. For the first one, the Philae protocol is just the functionality of ice latitudinal EBM tenacity. So it's a protocol and intercomparison project from the Cuisines project. And what they want is to do an intercomparison of different EBMs. And the first benchmark case is to achieve global mean surface of 288 kelvins. And that's what we did. And we looked for what are those values. And we found many possibilities, but this one I'm showing you here is just the eccentricity of 0.45, an obliquity of 3 degrees, a precession angle of 90 degrees, and a partial pressure of CO2 of 7 bars. We noticed that 7 bar CO2 is the one that gives the most stable climates throughout the different bars, partial pressure of CO2. In here, I'm just showing you how in the first panel is the insolation is being received per latitude. On the top right panel is the surface temperature, how it varies. On the bottom left is the ice mass balance, meaning that a clear color, ice is being deposited, dark color, ice is being lost. And on the right, we have the outgoing long-wave radiation. And what we see is that all of this correlates, so we have a validation of our code that it's working as it should. So that's why we wanted to do this as our first simulation. We're just trying to do kind of like a sanity check for our code. We then did a study of latitudinal temperature for various eccentricities. And here I'm just showing, remember that eccentricity is 0.45. But if we look at the error value of their calculation is plus minus 0.15 to 0.14. So if we want to study this to 3 sigma confidence, that means we had to do a range of 0.03 eccentricity to 0.9 eccentricity. So that's what I'm showing here, how the different temperatures of the planet vary through the 1 million year calculation. On the top one, it looks weird. Yes, it is weird, and it's because the simulation gets too cold, and it goes out of boundary for our simulation of the Williamson-Cassin. So that means that the planet is just really cold, and it doesn't get to run anymore because it just fell out of the boundaries. So for that one, the planet falls out of boundaries, a snowball state. The second one is we get a global mean surface temperature of 26 degrees. So it's really hot, meaning it's an ice-free state. And for the last one, we have a 0.9 eccentricity, but the planet gets too close to the star at the beginning. So it's so hot that it's just fall out of boundaries from the other side. However, because the planet eccentricity is so long, that means its winters are very long. So when we were able to lower the eccentricity so that the code could run, we see that the global mean temperature is about 6 degrees. So it's not that warm. So we get a snowball state, even though it's a global temperature of 6 degrees. Solution simulation 3, and I'm almost done. This is just a parameter sweep of eccentricities and obliquities, how those eccentricity and obliquity affects the state of the planet. We see ice-free is the dark blue, snowball will be the gray part, purple is the polar ice caps, and the outer boundaries is the region whether it's too hot or too cold. And we see that at least polar ice caps are formed. This is important because Earth has ice caps, so that's what we're trying to achieve if we can see ice caps in the planet. So this shows that for different eccentricity and obliquity, that happens. And we look at the global mean temperature for those different eccentricities and obliquities, and we get a 14.85 degrees Celsius at an eccentricity of 0.4 to 0.5, regardless of the obliquity. So we get kind of like a stable climate, regardless of obliquity for different eccentricities. Lastly, we did a parameter sweep of this time, instead of changing eccentricity, we changed the CO2. And we also see that polar ice caps are formed. And on the right side, we see that how many of those simulations are either polar caps, ice-free, or snowball. And we see that a lot of them are ice-free and snowball. There's very little of polar caps, but there is still a glimmer of hope because they still form. So that's a good thing that happens. And then I'll leave you to the conclusions. So I just want to cut it there. But in essence, we did find temperature conditions that can give a temperate climate, such as pre-industrial Earth. 7 bar CO2 would suggest that is the most stable one to create those polar ice caps. Most of the planet states are found either ice ball or snowball, and precession angle does not impact much the ice state of the planet. And we don't need direct observations to assess the habitability of GL514b. And I'll leave it there. Thank you.
Thank you, Héctor. So we have time for one quick question.
Great talk. So it seems like you're suggesting that a snowball state is a permanent state, and I'm curious as to whether or not your simulations show any deviation from that, because we know that that's a state that has been in flux on our planet. So I wonder if your simulations can account for coming out of a snowball state.
Yeah, so at least the simulation, what it's showing is that what I'm showing here on this histogram plot is the last state at the end of the simulation. But papers have shown that 1 million years is a good enough time for simulations for climates to stabilize. The thing is that because we're doing a static evolution, we don't expect it to change. But if we add the dynamic part, which is like changing in obliquity and eccentricity and precession angle while we're evolving the planet, then that could change. And it could have been like a snowball state at one point and then change to something else. But for the static ones, we're not expecting this to change since there's not much fluxes. Yeah. I think that's it. Yeah.